Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Shifted Inverse Power Method. The shifted inverse power method is a numerical algorithm used to find eigenvalues and eigenvectors of a matrix. It targets specific eigenvalues efficiently. It is a clever way to zoom in on a specific eigenvalue of a matrix, apart from the largest or smallest one, but a particular one near a chosen value, alpha, called the shift. Instead of working with the original matrix, it is slightly shifted by an alpha value to be closer to the sought eigenvalue. It is a variation of the inverse power method, which is itself an improvement of the power method for computing eigenvalues. The method is based on shifting and inverting the eigenvalues. Consider a non-singular matrix A whose eigenpairs are lambda I, xi for all I, and the matrix A has distinct eigenvalues with lambda 1 with the largest in magnitude. Shifting, for a constant alpha, the eigenpair of matrix A minus alpha times I becomes lambda I minus alpha and xi. Inverting, the eigenpair of inverse of matrix A can be expressed as 1 over lambda I and xi for all I. First employing shifting by alpha not equal to lambda, and then inverting, we find the eigenpair of inverse of matrix A minus alpha times I as follows. If alpha is chosen for an arbitrary lambda k such that alpha is very close to lambda k, see the figure, then the eigenvalue of the inverse of matrix A minus alpha times I closest to alpha will be the largest one. In other words, mu I goes to infinity as alpha goes to lambda k, while the remaining eigenvalues, mu I equals 1 over lambda I minus lambda k, are finite. Now, starting with initial vector x0 provided that its norm is 1, a sequence of eigenpairs can be obtained by solving the following matrix equation iteratively. Solving the linear system of equations gives the eigenvector estimates. A smart strategy to solve the linear system of equations, in this context, is to employ LU decomposition of the matrix A minus alpha times I. Once we obtain the L and U matrices, we can start the iteration process with an initial guess such that the infinity norm of the initial guess is non-zero. The system is then solved by a forward elimination, followed by a back substitution. This process significantly reduces the solution of linear system at iteration step. A new estimate for the largest eigenvalue, an absolute value, is computed from, where prior steps' eigenvector estimates are calculated by. The iteration procedure is continued until the stopping criterion is met. Finally, the corresponding eigenvalue of matrix A is obtained from, where mu1 is the dominant eigenvalue of the inverse of matrix A minus alpha times I. The convergence rate of this method depends on how fast the power of the dominance ratio yields 0 as p goes to infinity. The asymptotic error constant in the vicinity of alpha very close to lambda k can be written as follows. The method converges faster with the choice of alpha very close to lambda k, as the dominance ratio gets small. It is clear that lambda k does not necessarily need to be the largest or smallest one. It can be used to determine any desired eigenpair of matrix A. Having cast the eigenvalue problem as inverse of matrix A minus alpha times I, x equals mu x, The inverse power method is generally employed to determine the dominant eigenvalue and its associated eigenvector. The advantages of the shifted inverse power method are: the inverse power method is easy to implement, targets the smallest eigenvalue directly. It can provide very fast convergence in cases of symmetric matrices. It avoids explicit matrix inversion. It requires low storage. It is also suitable to find complex eigenvectors. The disadvantages of the inverse power method are: it requires the matrix to be invertible. Only one eigenpair can be determined. The approximate value of the desired eigenvalue needs to be known in advance. The rate of convergence may be slow if the eigenvalue is not well separated from others. The convergence speed depends on the initial guess. Let us consider the following matrix. We would like to determine the eigenvalue closest to alpha equals 25 using the shifted inverse power method with the Rayleigh quotient algorithm. We will use 0.5 times 10 to the minus 6 as the stopping criterion and a vector of 1s as an initial vector to start the power iteration. The inverse power iteration step requires the solution of the following system of linear equations in matrix form. For alpha equals 25, the shifted matrix can be written as follows. The shifted matrix will remain unaltered throughout the iteration process. Therefore, to minimize the computation time of the solution of the system of linear equations, we decompose the shifted matrix, which gives. Then we solve the lower and upper triangular systems of equations at every pth iteration. We begin with the initial guess vector and solve the lower triangular system, LZ equals x0, using the forward substitution algorithm, which gives. Then we solve upper triangular ux1 equals z using the back substitution algorithm, which results in. The inner product of eigenvector estimates x0 and x1 yields minus 0.461,364, while the inner product of x0 by itself gives 4, from which mu is calculated to be minus 0.115,341. The lambda eigenvalue estimate is found as 16.3300 and 5. The current eigenvector estimate is normalized before the next iteration. We begin the second iteration with the normalized current eigenvector estimate x1 and solve the lower triangular system, LZ equals x1, using the forward substitution algorithm gives. Then, we solve upper triangular ux2 equals z using the back substitution algorithm, which yields. The inner product of eigenvector estimates x1 and x2 yields minus 1.88536. The inner product of x1 by itself gives 1.968,946. Which leads to the mu2 value of minus 0.95755. The lambda 2 is then obtained as 23.955,668. The current eigenvector estimate x2 is normalized before the next iteration step. We repeat this process for the third, fourth, and subsequent steps. The eigenvalue estimates improve significantly at each step. This iterative process continues until the difference between the eigenvalue estimates and the norm of the displacement vector is less than a preset tolerance value. The iteration process results in 6 decimal place accurate estimates in 7 iterations. The closest eigenvalue to 25 is found to be 24, and the associated eigenvector is 1, 0, -1, 1. With this note, we conclude this video lecture. That is all for now. See you next time with another topic. Bye.